For this example, we'll look at a scenario where we've got a dead load and a live load of 1,000 kilonewtons each. Our column is a 500 millimeter by 500 millimeter square column. Allowable soil bearing pressure is 250 kPa. Allowable soil bearing pressures vary from the really low end of about 100 kPa up to, if you're sitting on really, really solid, almost like rock configuration, getting up to sort of 700 kPa. So the 250 MPa here is towards the low end, but it's kind of a loose fill kind of scenario. Also, what's quite common with a footing is to use 25 MPa concrete. Even though you might use 35 MPa concrete for the rest of the structure, the footing is often using a lower quality concrete. And the reason for this is cost. Now, when we get into our calculations, we end up with a relatively large footing. Again, this is based on not exceeding the allowable bearing pressure of the soil. So what that means is a fairly large volume of concrete. And then because we want to avoid shear, we end up putting in something that's fairly deep as well. So again, a fairly large volume of concrete. Now we also adjust things like our cover distance on here. Cover distance, remember, for a slab went down as low as 20 millimeters. It could be up around 40 millimeters for a beam typically, 40 to 60 depending upon the kind of environment you're in. But here with a foundation, it's quite common to have cover distances, and code specifies 75 millimeters kind of as a minimum, but you can actually have more like 100 millimeter cover distance. And part of that is because you're pouring this concrete right on top of the ground. Right? You're not exactly building formwork like you are with a beam. Right? So you have less control over what that ground profile is. Now you're sure you'll throw some gravel down there and you'll compact it, but there's still going to be some variations in there. So the larger cover distance will allow for that kind of variation within the fill profile as you put it in there. So with a large area, a large thickness, and increased cover distances, that's a whole hell of a lot of concrete. So why not put the cheapest stuff in? We're not needing it from a strength perspective. So it is quite common to use 25 MPa for our footings. And then 400 MPa is our standard for rebar. So again, what we'll do is we'll start by coming up with an area calculation. So there's total load unfactored, and divide by 250 kPa. So again, kilonewtons, kPa is giving us an answer here in meters. So now we're going to get an approximate size just by taking the square root of that. So the square root of 8 works out to be 2.83, so we're going to round up. Round up and go with a 3 meter by 3 meter. Now we know what size we're dealing with. We're going to figure out what is our factored soil bearing pressure. Again, that QF is going to be necessary to do these shared moment diagrams, shared moment calculations. Right, so our actual area is 3 by 3. 9 square meters. Our PF, 1.25 dead, plus 1.5 live, which works out to 2750 kilonewtons. So our QF, 2750 divided by 9. 305 kPa. Yeah.
That Q allowable, is that does it include the soil on the top?
That's right. So from our perspective here, we're considering that to be net.
So that one's net.
Yes. Yeah, in our example here, we're not looking at the depth of the foot. That's kind of a separate calculation that fits in more of the earthquake stuff. Okay, so next we're going to go, so we calculated our area, come up with our QF, so now we're going to do our shear check. So we're going to start with our two-way shear. So I'm going to start with this BC, 0.38 lambda by C F prime C. And this is, this is equation 13.7 in the code. Now, as I mentioned, so if you go and look up equation 13.7, you'll see there's also an equation 13.6 and equation 13.5. They're both related to calculating VC. This is lowercase v, by the way. Right, so you'll notice here it's coming out in MPa. Right, so there are three equations that are listed in the code, and it is commonly assumed that this is the one that governs. If I've got kind of a standard configuration, square column, square footing, bending is exactly the same in both directions, nothing's out of the ordinary, then usually this equation is in fact the governing. So we're not going to go check the other two equations for this example, but if you... Pardon me?
You sure it's 13.7?
Page 108.
Paper. Equation 13.
It was around like that. Yeah.
13. Page 108.
Yeah, 108. So it's, so this whole section is 13.3.4 in the code. Right, so there are three equations listed there. We're just looking at the third equation, commonly assumed to govern. Right, and if I've got a rectangular or some other kind of configuration that is outside of normal, it's possible one of the other ones to govern. Right, so we're just going to calculate based off of this one. First we plug some numbers in. Now what we're going to do here is we're going to set BC equal to BF, which is our 2750. Right, now here we're looking, because we're talking about the punching shear, we're looking at the full force punching through. We're not calculating V at a distance from the edge of the column facer. Yes?
Is that little BC or big BC?
This is big. Right, this is little, this one's big. Want to do that? So what I'm going to do now is I'm going to, again, remember the formula here is big BC is little bc times the area that it punches through. So that's that perimeter around the column, and then we have our D in here. So what I'm going to do is plug this into there, along with this formula right here. So let's calculate our little bc here. So 0.38. Lambda is 1 normal density concrete. Our phi C is 0.65. We have square root of 25 MPa. We end up with 1.24 MPa. So like we did with our other area calculations here, when we're working with concrete and soil pressure in particular, it's quite common to work in KPA. So you see these values coming in. KPA is reasonable size. Like often when we're working with steel and concrete, we're talking about MPA, but now once we're getting into the soil, it's quite common to talk about KPA. So this is 1240 KPA. So what I'm going to do, plug all of those in, and we end up with D0. D is big BC over little bc. Now what we've done here is we've isolated our V0 term, or V0 and the V term, so the parameters that relate to the geometry of the of our footing. So remember that for our two-way shear, this is based on D. Not only is it based on D here, but our B0, that perimeter that we were talking about, is calculated at a distance of D from the support, or D over 2 from the support. Right? So again, let's just sketch this up. We got our footing here, we've got our column here, and what I want to do is deal with this area right here at a distance of D over 2. This distance here is D over 2. Right? The length of this line is our B0. Right? Well, we know the width of our column. Right? So the width of our column is 0.5 of a meter. Right? I'm going to label this dimension here T, the thickness of our column. Right? So I can generate an equation for B0, right? That's the length of that blue line. So I've got 4 sides and T plus D. Right, so D over 2 is on this side plus D over 2 on that side, so a total of T plus D, and I got 4 of them. Right, so we can come up with an equation. So B0 is in turn based on D as well. So I'm going to stick that now into this equation and come up with a calculation which will allow me to solve for D directly. So our B0 times D is 4 times 0.5, plugging in a value for T, plus D times D. And we want to set that term equal to our 2.22 square meters. And what that gives us here is an expression, 4D squared plus 2D minus 2.22 is equal to 0. And I get a quadratic expression in terms of D. Again, though, we need one root that makes sense. So we get 0.544 meters. The other root out of this particular equation is negative, right? So there's only one root that's going to make sense. In fact, the only root that you really want here is the smallest positive number. So now we have a value for D. I'm going to go back into our calculation here and
Question. We formerly had down over there that one. Why did we add extra D over there?
right, because what we've got here is we've got our T distance here, plus a D over 2 on this side and a D over 2 on this side.
Okay.
Right, so it's T plus D, right? So that's the length of one side, and we got 4 of them.
So for a wall, you have on the left side 2.
For a wall, we don't have two-way bending.
Oh, yeah, that's right.
So for a wall, we just go straight for a 1 meter wide design strip and do it like a slab, and we're just calculating our one-way shear only. Right, so now I know D. Now, with a value for D here, we can calculate our H based on our cover distance. Right? So our H is going to be our D plus our diameter of the bar plus our cover distance. Right? And 540 millimeters. Right, there's our D that we plugged in here. Plus, now here we're going to guess a bar size, so I'm going to try 25 M bars. So I'm going to put in 25 over 2. And then cover distance of 75. 628 millimeters squared. Now, I could have also, in this calculation, added another 25. Right? And in fact, normally I do, but we're going to round up this number anyway. We're not going to leave it. We don't specify the thickness of 628. So we're going to round that up anyway. What we've got here is the distance from the top down to that first row of reinforcing. Well, in the other direction, the bars are going to be slightly higher. And they're going to be higher by another 25 millimeters. Right? So in our case, if we round this up to 650, we're pretty good. right? I'm not going to worry about that extra 3 millimeters, it's close enough. Right, remember we've got some variation in there and a much higher cover distance here as well. So I'm going to use H of 650. So we've started by calculating our area. So we got our area. Now we come up with a thickness based on two-way shear. Now we got H and D. So I can use this now to calculate our dV value. Remember, dV is one of two formulas, either based off of H or based off of D. So we can now go through and do our one-way shear calculation. And so this is just a check to see if it works. And if it does work, then we're good. If not, we'll increase the thickness and go through our iteration.
Are we always going to use 75 for coverage?
For foundations, yes. Okay, so again, what we want here for our shear, let's just and we want to come up here and find VF here. Right, so there's we had 500, so this is 250, and then this distance here is dV. Right, so again, this dashed line here represents the edge of the column, and we're going away from the edge of the column another dV value. So what I want to do is come up with the value for VF, right? And this is just based off of similar triangles. So our VF works out to be QF times D times B minus T over 2 minus dV. Right, this is that equation in here. This is that part where I make that reduction factor at a distance of dV away from the edge of the support. We've seen that calculation before, right? So here when you're plugging it in, I use the same terminology, T as the thickness of the column, right? So we come up with an expression here which allows us to solve for VF, right? So it's not the peak, it's this value down here at dV from the edge of the column. So as I plug in, we had 305 kPa here. Our B value, we're using 3 meters. 3 minus 0.5 over 2, and then minus another 0.5. And we calculate here 686 kilonewtons. Now we'll calculate our dV.
Can we just use dV and then plug that?
Hang on. Oh no, this is yeah. Yeah, no, it's, we should actually adjust that. Yeah, let's calculate our dV first, and then we'll go back and revise that here. So dV. So it's either 0.9D or 0.72H. 0.9 times 550 or 0.72 times 650. So we'll get 495 or 468. And this one here governs.
What's in D for 540?
So this will be this one here, 495. I don't think it's going to change that number really.
D not 450?
540.
So what you're noticing here is that our calculated value for D, when we went through and used our formula to come up with that value for D, we used that and then we increased our thickness of our footing in order to round up to a convenient number. So basically what we've done here is for the 550 that's in here, right, I'm taking 650 and I'm minus 100.
Peter, wasn't D 5 point, like
0.54 meters. We,
Yeah, so what we've got here, 0.54, yeah, so now we've gone 0.55, we've increased the value because we increased the thickness of the footing.
okay,
Right, so we had a calculated value of what is the minimum D that we need, right? And then from that, we added a bar, and we added cover distance, and then we rounded up. So as soon as I round up to recalculate D, basically what we do is we take our new H, and then we subtract our cover distance and our bar diameter, right? So this value right here is 100 less than that. Right, so this is a quick shortcut which is often used in footing design. If I'm using a 25 M bar and my cover distance is 75 millimeters, right, and what I've got is 75 plus 25 to get me that 100 difference, and that gives me the centroid of our reinforcing steel, which is actually right in between the two rows of bars. So this is a shortcut approximation that is often used. Just take that number, subtract 100, and I've got a new D.
No stirrups.
No stirrups, that's right. We're trying to design this without the stirrups.
with the chairs?
The chairs, yeah. I was actually I've got some samples back in 110. So they're little cement-based devices that you just put them on the ground, and it raises it up, and you place a bar and a little bit of a hook there. There are some plastic ones available as well. It is preferred to use ones that are now made out of cement because the modulus of elasticity of the cement is closer to that of concrete. So there's no real aggregate in it, but yeah, it just stays in there and becomes part of the footing and just holds it in place. Okay. So we're going to go and do our one-way shear calculation. So we've now got a value for dV, right? So again, our 495 governs, right? So we can use that as 0.5 as an approximate value, close enough. So what we're going to do is plug into our calculation here. So dV we now know, VW we know, F prime C we know our phi factor and lambda as well. So the last thing we need to calculate is our beta. So again, beta is 1,000 divided, or 230 divided by 1,000 plus dV. So beta is 230 divided by 1,000 plus dV. And as I plug in 495 millimeters into here, this works out to be about 1.5. So now I can stick everything into our VC formula here. So 0.65, lambda 1, beta 0.15, square root of 25. We're looking at 3 meters, so 3,000 millimeters here. And then times 495, and times 10 to the minus 3 to turn that into kilonewtons. So much like our other shear calculations that we went before. Right, I got F prime C here, in MPa, millimeters and millimeters. This is coming out into newtons. Right, so 10 to the minus 3 there converts that to kilonewtons. And we end up with about 730 kilonewtons. I compare that to my VF that we've calculated here, and see that this is bigger than VF. So bigger than VF. So okay. Right, and again, if it's not bigger than VF, what we want to do is increase the thickness and try again. Now, depending on how close you are, you might just want to try another 50 millimeters. Right, so we've you're not going to put in a slab that's 662 millimeters thick, right? You're always going to round up to at least 25 millimeters. It's more likely 50 millimeter increments.
Is there a
right?
ratio to that, or is like can you ratio it off the thickness of the 730 or?
Not really, because there's you know, your beta term is dependent upon dV, right? And dV is greater of two separate formulas, right? So you can approximate by a ratio. Because when you're looking at the formula, what you're seeing is, if I change dV here and leave nothing else out of here, right? So if I increase dV by a ratio, right, that'll get pretty close, but technically this number changes as well, right? And so yeah, you can use that ratio and come up with an approximate and then try it, Right? But generally speaking, you're going to be reasonably close after having done your two-way shear. Even if it doesn't work with a one-way, you're going to be close. So we tried 650. If that didn't work, then I would try 700. Right? Or maybe 750. Right? And again, if you're doing this in a spreadsheet, all you do is just change that number and you iterate through as you go. So we've now gone through and done our shear check. So next, we're going to take a look at our moment calculation.